2.4 codes as the form of spreading signals. To spread the transmission bandwidth, the signal must be modulated with a spreading signal that is significantly faster than the information signal, thereby delivering it through a much wider bandwidth. However, while it has been determined that the spreading signal is a pulse signal that changes much more rapidly than the information signal, the actual content of that signal, meaning its specific form or shape, has not yet been established. For example, in the case of a voice signal, the signal carries vocal information, and in the case of video data, there is a pattern of signal variation according to the visual information. It has no other function than to spread the signal, so it possesses no distinct characteristic in its form. One of the most important tasks we must undertake is to specify the form of this spreading signal. In other words, we must determine what kind of content should be applied to the spreading signal. This is a matter of deciding what kind of clothes to put on a naked person. The content of the spreading signal utilizes a sequence of 0s and 1s generated in a constant pattern. This is referred to as a sequence in English, and it is also called a code. In the case of is-95, a representative CDMA system, PN codes are used, while in WCDMA, the European-style next-generation mobile communication gold codes are used to create the spreading signal. 2.4. One linear filter. A device that produces a constant output for a given arbitrary input is called a linear device. In other words, in a linear device, the input and output are precisely paired. This means that there is a predicted output corresponding to the input. That is, a device for which the output can be anticipated is called a linear device. Furthermore, such characteristics are referred to as linear features. It is very important to determine whether the system we intend to analyze is a linear system. Therefore, we must first provide an explanation regarding linearity. If we express linearity as a function, it would be something like a first-order function. In other words, it is often explained by saying that the response of the function takes the shape of a straight line, which is the graph of a linear function. If that is the case, are functions represented by quadratic functions, trigonometric functions, logarithmic functions, or even derivative functions not linear? Let's consider a quadratic function, as an example. Since we have thought of only functions expressed as y(b) as linear, we would have to say that a function expressed as y3x cubed plus 3 is not linear. More accurately, in this function, y does not show a linear response with respect to x, that is, it is not a linear function. Therefore, we must say that the function yx square is a non-linear function. If the condition for being a linear function is that the input and output must have a first-order functional relationship, we can find a new meaning for this requirement through a new approach. If we substitute 3x squared plus 3 with t in the mathematical expression above, the equation becomes yd. That is, if we draw a graph by substituting the x-axis with an axis for 3x squared plus 3, the dependent variable y, and the independent variable, 3x squared plus 3, are plotted as a first-order function. From this point forward, we can say that y is a linear function with respect to t. Just as we substituted 3x squared plus 3 with t in the mathematical expression, we can substitute various polynomials of x with t. By extending this concept, all expressions can be represented as first-order functional equations. The discussion so far implies that any function represented as y(f(x), etc., can be transformed into a linear form, and described as linear with respect to the substitution variable t. Naturally, systems that can be represented by such functions are linear systems, where inputs and outputs are precisely paired, allowing the output value to be predicted based on the input value. As we discussed, being able to fully explain the characteristics of an arbitrary system with a mathematical function means that we can represent the function that defines the correlation between the system's input and output. Therefore, we should understand that the concept of linear in mathematics or science carries the very important meaning that cause and effect are proportional according to a certain rule, and are thus predictable. It goes without saying that the certain rule mentioned here refers to the polynomial substituted with t in the mathematical expression. Natural sciences such as mathematics, physics, and chemistry observe and interpret natural objects or phenomena. By adding human needs to these observations, they evolve into engineering. The essence of all academic disciplines, including engineering, is to interpret appearing phenomena. This interpretation process involves obtaining general facts through inductive logic, and further inferring new facts by using deductive methods as conclusions for specific facts. However, the inductive method is a process of generalizing predictable cases. For instance, because the sun rose in the east today, we can predict that it will rise in the east again tomorrow. In this regard, all academic disciplines based on inductive reasoning are limited to the scope of what is predictable. For example, we can predict that a vacuum cleaner will operate when the power switch is turned on, and if it does not, we can diagnose it as being broken. This is because a vacuum cleaner is a linear system. However, if Chol-Soo tries to use the vacuum cleaner and it doesn't work, we cannot definitively say or predict that the vacuum cleaner is broken. This is because Chol-Soo, who is using the vacuum cleaner, is a non-linear system. While we can manufacture a linear vacuum cleaner in a factory, we cannot manufacture a non-linear being like Chol-Soo in a factory. In summary, all functions where the relationship between the output and the input can be expressed as y(f) or f, that is, systems where the relationship between output and input can be perfectly analyzed through constant principles and structured into mathematical equations, should be defined as linear. In this regard, anything defined by the functions we can represent mathematically can be called a linear system. To put it another way, things that we can control and create should be referred to as linear systems, and furthermore, as linear devices. As a result, linear is a term that represents the domain which we can either create or control. In contrast, non-linear devices do not have a fixed pairing between input and output. In other words, non-linearity refers to a state where there is no determined output value for the same input value. In this sense, non-linearity is a concept that encompasses things we cannot finalize, things we cannot assert, and things that have no specific trend. For instance, a romantic relationship is a non-linear relationship. A partner who used to love it when you bought her delicious spaghetti might not be happy, even if you buy her the same spaghetti again. Conversely, linearity refers to a state where we can predict and assert changes or trends, meaning the response or result to an input or stimulus is deterministic. Therefore, a system with linear characteristics is controllable. A clock, where the second hand invariably moves once you replace the battery, is a representative example of a linear system. In physical systems handled in mathematics or engineering, the most crucial perspective is whether humans can control them or not. However, since most systems in the natural world exhibit non-linear characteristics, most scientific and engineering processes treat them by approximating them into a controllable linear domain. The spreading signal we intend to create must be as random as information data like voice or images. However, because we must generate this spreading signal through a linear filter where the expected output is determined by a given input, we cannot create a completely random signal. For this reason, the output of the linear filter we design is called a pseudo-noise signal. As mentioned earlier, we cannot create a non-linear system to obtain a truly random output. Let's consider a shift register where a binary value is output one clock cycle after it has been input in synchronization with the clock. In other words, a shift register stores the initially input value until the clock pulse arrives, after which it transfers that value to the adjacent register. This is why it is called a shift register. If two of these registers are connected in series, the input value will be output only after two clock cycles have passed. Now, let's consider a system where a larger number of registers are connected in series. In this case as well, each time a clock pulse is input, the registers will transfer the values they were storing to the registers connected right next to them. The registers located at both ends of this connection can be thought of as the system's input and output stages. Furthermore, the registers between the input and output can be referred to as the system's internal registers. Now, we are going to obtain a new response from the system through a slight change in the connections. First, consider taking the values being transferred by the internal registers, those situated between the input and output stages, and performing a modulo -2 addition on them along with a output value, then feeding that result back into the input stage. In this context, extracting values from the internal registers means that we are not simply feeding the output back into the input. Rather, to determine the signal to be fed back, we are reflecting both the signal being output now, and the signals that will be output several clock cycles later, the intermediate values. In practice, the input and output will vary depending on which intermediate values are selected. Thus, a device composed of shift registers and modulo -2 others is a linear filter that outputs a unique value corresponding to the original input at every clock cycle. A linear filter consists of a parity generator which is composed of exclusive OR gates and N shift registers that serve as delay elements to lag the input value by one clock cycle. Because this specific configuration feeds the values of the N shift registers back into the system, it is specifically called a linear feedback shift register. The codes output from an LFSR, which is a linear system, are linear codes. The general structure of an LFSR is shown in Figure 2.15. Each SR transfers its stored value to the next stage every time it is lashed by the clock. Additionally, that value may or may not be fed back into the input. These feedback values are connected to the PG, where they undergo modulo -2 addition to determine the new input for the LFSR. An LFSR that outputs a constant sequence or linear code is determined by its input. Furthermore, since the input is determined by the values of the SRs being fed back, the output of the LFSR depends entirely on the connection state of the shift registers. 2.4 To generator polynomial. An LFSR consists of N shift registers with different delay values. If we denote the value stored in each SR stage as x, and use an exponent to represent the number of times that value has been delayed, we can express the values of the N SRs. For example, the value of an SR delayed once is x to the power of 1, or simply x. The value of an SR delayed twice is x to the power of 2, and the value of an SR delayed n times can be represented as x to the power of n. Furthermore, the values of the SRs connected to the modulo -2 adding PG are reflected in the input and can be marked as 1, while those not connected can be marked as 0. Now, the output value can be expressed as a function of x variables that determine the input. Representing the relationship between the input and output of a linear filter, LFSR, as a polynomial in this manner, is called a generator polynomial. In an N-stage LFSR, the input value being fed back representing 0 delay is x to the power of 0, which equals 1. Therefore, a plus 1 inch always appears in the generator polynomial. An N-stage LFSR is often abbreviated as an NLFSR. Meanwhile, if the value of the final NTH stage SR did not contribute to determining the input, it would not be called an N-stage LFSR. Thus, since the NTH stage is generally always fed back, the form of the generator polynomial for an NLFSR is x to the power of n1. Figure 2.16 shows a 3LFSR where the outputs of the first and third SRs are fed back, undergo a modulo -2 addition, and the result is fed into the input. The generator polynomial G for this linear filter is x cubed plus x plus 1. A 3LFSR consists of 3 SRs, and the values within these 3 SRs represent the state of the LFSR. For example, if the first SR, which stores the value delayed once, is 0, the second SR is 1, and the third SR is 1, the state of this LFSR is 011 inch. In this manner, a 3LFSR can have to the power of 3, or 8 possible states. We can extend this logic. An LFSR can have to the power of n-1 possible states. Since the state of an SR is either 0 or 1, the range of states an LFSR can represent is a finite range determined by the number of SRs included in the LFSR. This can be thought of as a Galois field GF, which specifies a finite range. To touch briefly on the concept of a finite field, a set of numbers where the number of elements is finite is called a finite field. Therefore, a set of real numbers from 1 to 5, or the set of all natural numbers, are not finite fields because their elements cannot be fully counted. In contrast, a set of natural numbers within a limited range is finite. Similarly, a set up to the power of 3 consists of natural numbers from 1 to 8, making it a finite field with a finite number of elements. Furthermore, while a set of numbers expressed only as a series of primes is not necessarily a finite field, a set that defines its maximum value through a specific prime power is called a Galois field. Thus, a Galois field is a finite field. Meanwhile, if all states of an NLFSR are 0, the input value will always be 0, regardless of which values are selected for feedback. Consequently, there will be no change in state. Since the LFSR would no longer transition once it hits the all-zero state, the all-zero state must be excluded from the possible states. Therefore, the actual number of states an LFSR can cycle through is 1 less than GF to the power of n is to the power of n minus 1. 2.4. 3 primitive polynomial. Now, let's consider the state transitions of a 3-stage LFSR. If the current state is 011 inch, and A1 is input during a clock latch, the state changes to 101 inch. Since there are 7 possible states for a 3 LFSR, it can theoretically transition through 7 different states. However, it is rare for an LFSR to be able to transition through all possible states without exception. For a 3-stage LFSR, the possible generator polynomials are x cubed plus x squared minus 1, x cubed plus x plus 1, x cubed plus x squared plus 1. When the initial value is 111 inch, the state transitions of the LFSR for each polynomial are as shown in table 2:1. While the second and third polynomials transition through all 7 states without exception. The first polynomial ceases to transition once the SR state progresses and falls into the 111 inch state. Meanwhile, since there are 6 more initial states besides 111 inch, one could check how it operates for other states. However, if it transitions into the 111 inch state after repeated transitions from any arbitrary state, the transition stops. Thus, this polynomial can no longer represent all numbers belonging to the finite field of the LFSR, that is, all states without exception. Figure 2-17 shows the states that appear for the first generator polynomial, x cubed plus x squared plus x plus 1, when 3 different initial values are given. That is, it shows the subsequent state transitions following the input when 111 inch, 010, and 110 are set as initial states. The characteristic appearing here is that it is composed of 3 separate cyclic loops, and these loops cannot connect to one another. On the other hand, the remaining 2 polynomials output all elements on the GF to the 3 Galois field included in the 3 LFSR. The 3 SRs of the LFSR, expressed by the second and third generator polynomials, transition through all 8 states without exception, and have a cyclic characteristic of returning to the original state. This indicates that for any arbitrary SR state, there always exists a previous state, and a state to proceed to. Also, the fact that state transitions are cyclic means that no matter which initial value you start with, the cycle of returning to the initial value after passing through all states is maintained. Codes output from an LFSR with these characteristics are called cyclic codes. Generally, generator polynomials that can represent all elements of a finite field are extremely limited, but it is known that at least one exists. Such a generator polynomial is called a primitive polynomial. In other words, the output of an LFSR, which is a linear filter using a primitive polynomial as its generator polynomial, is a cyclic code. And since a cyclic code transitions through all possible states of the LFSR without exception, the code word generated during the transition process is the longest. That is, a code generated using a primitive polynomial, as the generator polynomial, is the M sequence with the longest code word. Since the length of the M sequence is the length of the transitioning states, it generally has a length of 2 to the power of n, 1 for an NLFSR. An NLFSR with length n that creates the M sequence outputs the M sequence while passing through all states. This also means that an NLFSR creating the M sequence by passing through all states has the maximum number of candidate states for the next transition from any arbitrary state. Furthermore, this implies that the next state cannot be easily predicted, making it random. When the length of the linear filter LFSR is long, that is, when n is large, the number of states the LFSR can transition to increases, and thus this randomness increases. Consequently, if the length of the linear filter is very long, and the generator polynomial of the linear filter is a primitive polynomial, it is possible to obtain an output with noise-like randomness, even though it is a linear filter designed by us. 2.4 for maximum length sequence, M sequence. The M feedback that allows the linear filter, the LFSR, to transition through every possible state without exception. Its length corresponds to the finite range of numbers the linear filter can represent, which is the total number of possible states. Here, the feedback combination of SRs refers to the generator polynomial that defines the structure of the linear filter by indicating whether internal SR outputs are connected for modulo -2. Additionally, the finite range of numbers refers to the generated code length to the power of n-1. In an NLFSR linear filter, there can be to the power of n possible generator polynomials, depending on the connection status of the n shift registers to be fed back. However, since the case where no SRs are fed back must be excluded, there are practically to the power of n-1 possible generator polynomials, which is equal to the length of an M sequence. A cyclic code is defined by having a cycle as its modulo. In other words, the fact that state changes by a generator polynomial circulate without exception means that when divided by the cyclic period, that is, when taken as a modulo, it divides perfectly, without a remainder. For this reason, a generator polynomial that divides evenly into the maximum period is a primitive polynomial. So, how do we express this maximum period? An NLFSR creates a finite field with to the power of n finite elements. However, since no state transition occurs regardless of the input when all SR states are 1, the case where all SR states are 1 must be excluded from the finite field values. Therefore, the number of elements a finite field can have is to the power of n-1. The maximum length of a finite field is modulo 0 of the finite field. When the current value is the same as the initial value, it is unclear whether it is the very first value, or a value that has appeared after completing one or several cycles. However, it is clear that the appearing value is the same as the initial one. This implies that the current value is independent of the feedback process, meaning feedback no longer occurs, and the input value is output as is. Therefore, algebraically, this is expressed as x-1. A generator polynomial is a case where it divides into this period with a remainder of 0, meaning it divides perfectly. For example, amongst generator polynomials of A3LFSR, the primitive polynomial P1 equals x cubed plus x plus 1 divides perfectly into xn1, which represents the period of the finite field, with a quotient q1. In this case, q1 equals x to the fourth plus x squared plus x plus 1, and there is no remainder. Thus, the polynomial P1 is a primitive polynomial, and outputs an M sequence. Of course, from the perspective of Q1, it could also be an M sequence since it is divisible by P1, but Q1, which includes x to the fourth, is not a generator polynomial for A3LFSR. The number of primitive polynomials that can appear in an MLFSR is represented by the Euler-Totient function, phi, as shown in equation to 20. That is, it is the Euler-Totient value of the code length to the power of m divided by the number of SRs, which are the delay taps. In equation to 21, pi represents the prime factors of the code length L. For example, in the case of A for LFSR, L15 and M4, since the prime factors of 15 are 3 and 5, according to equation to 21, phi 15 times 8. These are the 8 numbers smaller than 15, and relatively prime to it 1, 2, 4, 7, 8, 11, 13, and 14. Consequently, the number of M sequences for A for LFSR is 8/2. Table to shows the number of primitive polynomials according to the number of SRs, which are the delay elements determining the size of the finite field. Among primitive polynomials, those that take the form x to the power of m plus x to the power of k plus 1 are called trinomials. Here, k is greater than 1 and less than m. Using a trinomial, which has only 3 terms, as a generator polynomial offers several advantages in actual circuit implementation. In this case, since it requires only a single exclusive OR gate, regardless of the LFSR degree, the circuit is simple and low cost, and because there are fewer delay factors in the circuit, it is useful for high-speed operation. Currently, in Korea's CDMA mobile communications system, M sequences known as PN codes are used for base station identification, and personal identification, respectively. PN code is another name for the M sequence, meaning pseudo-noise, a random code similar to noise. Meanwhile, the PN short code used for base station identification is an M sequence generated from a 15-stage LFSR, which includes 15 delay elements. In other words, there can be 1,800 different configurations of PN code generation devices in a 15-stage LFSR. This is approximately 5.5% of the 32,767 possible generator polynomials when the number of SRs is 15. 2.4. 5 PN codes used for spreading signals. As we considered earlier, spreading signal does not contain any information. Its signal pattern does not inherently possess randomness. In contrast, the information reflected in a signal such as a voice or a drawing on a sketch pad determines the shape of the information signal, which can be described as almost random. For this reason, the spreading signal we intend to create must also possess similar randomness. However, if we think about it, the randomness of the information we create is not that significant. We speak in similar patterns and draw with similar or predefined colors. In this regard, the patterns of naturally occurring signals are somewhat lacking to be called truly random. The most significant characteristic of a spreading signal is that it has a much higher bit rate than the information signal. This speed is directly proportional to the degree of spreading. That is, to spread a signal over a bandwidth 10 times wider, the spreading signal must be 10 times faster. A faster signal means the degree of change is much more diverse. Considering these properties together, the form of the spreading signal is applied as a series of patterns or codes generated from an LFSR with a relatively long SR. Specifically, the code used here must be an M sequence. In this sense, the PN code, which is an M sequence, is utilized. The reason PN codes were used as spreading signals in the CDMA cellular system developed by Qualcomm and commercialized in Korea is not only for their diverse randomness, but also for their representative characteristics, autocorrelation and run properties. The fact that the spreading signal is a PN code means that the signal modulated with the PN code pattern possesses these autocorrelation and run properties. Now, let's examine these two characteristics. First is the autocorrelation property. Even if PN codes are generated from the same LFSR, they reach the receiver through multiple paths which may cause the receiver to mistake them for different signals. That is, even if signals originate from the same transmitter, they are received with different phase shift characteristics, as they experience different channel conditions. However, two PN codes that the receiver perceives as different are, in fact, the same code. Therefore, before demodulation, the receiver must adjust the misaligned phases of these two signals to make them identical. This is the general process by which a CDMA receiver acquires a code signal, and it is easily achieved due to the excellent autocorrelation properties of the PN code. Autocorrelation is a value that measures the degree of correlation with itself. It indicates how much a signal appearing after a certain period has changed compared to the original signal. Of course, measuring the changed value is done with the goal of compensating for that change. Thus, it refers to the correlation between two signals that were originally the same, but developed a phase difference for various reasons. The function to find the autocorrelation between PN codes is through the bitwise modulo -2 addition of the PN code and its phase-shifted version. That is, the difference between the two signals is calculated by summing all cases where the two codewords have the same value, and where they have different values. In the case of a PN code generated from an LFSR consisting of n delay elements, there are 2 to the power of n, 1 states represented by the LFSR taps, and 2 to the power of n, 1 code words are generated by those states. Since the state where all SRs are 1 is excluded, or more commonly, the all 0 state is excluded, the number of 0s and 1s in an M sequence codeword differs by exactly 1. Specifically, the length of a PN code is always an odd number. Bitwise modulo -2 addition between a PN code and its phase-shifted version creates a new PN code, which is a homogeneous PN code shifted only in phase. Thus, the correlation value between PN codes is the sum of all the resulting codeword bits. For this reason, when homogeneous PN codes of length 2 to the power of n 1 are out of phase, the autocorrelation value is the sum of the newly generated p encode. In this case, since the number of 1s is 1 greater than the number of 0s, the autocorrelation value is constant and low. However, when the phases of the two codes match, the autocorrelation value reaches its maximum at 2 to the power of n, 1. By using a p encode with such extreme autocorrelation values, the receiver can clearly distinguish the phase of the code based solely on the autocorrelation value. It should be noted that the cross-correlation between heterogeneous p encodes, those generated by different generator polynomials, does not appear as extreme as autocorrelation. According to Table 2, for SR5, there are 6 primitive polynomials that can generate M sequences. Among them, the cross-correlation between p encodes generated by x to the 5th plus x to the 4th plus x cubed plus x plus 1, and x to the 5th plus x cubed plus is shown in Figure 2.18. The cross-correlation between code sequences generated by A5LFSR does not show a stark difference between when the synchronization is misaligned and when it matches, unlike the autocorrelation of a p encode. On the other hand, Figure 2.19 shows the autocorrelation characteristic compared with the cross-correlation of M sequences. As seen in the figure, autocorrelation drops sharply, even if only one bit is misaligned. This is a superior characteristic compared to cross-correlation. The second is the run property. A run refers to the extent to which 1s or 0s appear consecutively in a codeword. In a p encode of length 2 to the power of n, 1, there is one run of 1s of length n, one run of 0s of length n-1, and for a run of length k, the number of 1 runs and 0 runs are equal, appearing to the power of nk-2 times. This means that long consecutive strings of 1s or 0s do not occur frequently. Generally, in the case of information data, the form of occurrence is random. This is characterized by the fact that the next value is independent of the previous one. It doesn't mean that because A1 appeared this time, A0 will appear next, or that 1s will continue to appear. Our search for a signal form suitable for spreading signals among codes is to find a signal with this kind of randomness, and the p encode run property demonstrates this randomness well. Compared to the total length of the p encode, the ratio of the longest run of identical values is only n2 to the power of n. As the code word length increases, that is, as n grows, this ratio decreases rapidly. For reference, in the case of a pn long code where n42, the length of the run of 1s, that appears only once in the entire codeword, is a negligible percentage. A31 length M sequence appears as 1111101000, 100, 1, 0, 1, 0, 1, 10000, 1, 1, 1001110. The run characteristics of this code are shown in Table 2.3. The code word composition of a PN code with these run properties has much clearer randomness compared to Walsh codes, which can be considered more artificial. Since Walsh codes are generated specifically to maintain orthogonality between codewords, runs of consecutive 1s or 0s occur frequently, and their lengths are relatively long compared to the total codeword length. 2.4.6 Walsh code. In 1923, J. L. Walsh defined a system of orthogonal functions where codewords are orthogonal to each other. Since the codewords are orthogonal, they are clearly distinguishable from one another. With this characteristic, Walsh codes are perfectly suited for channel separation in CDMA systems, where channels are not divided by frequency or time slots. Walsh codes are used to create channels in CDMA, and it is through these codes that the code channels of CDMA are established. Each Walsh code, as an orthogonal code within an orthogonal system, is used as a code channel and is identified by its code index. It is important to distinguish that the orthogonality of Walsh codes stems from the system requirement to separate channels, whereas the superior correlation of PN codes is intended to identify phase misalignments caused by the receiving environment. Codewords within an orthogonal function system must have an equal number of identical and different bits when compared bit by bit with another code. For example, when comparing the code 1100 with 1010 bit by bit, there are 2 identical bits and 2 different bits. Since the sum of the bitwise calculations between the 2 codes is 0, They are orthogonal. Methods for generating Walsh codes include using Rademacher functions, the symmetry of Walsh functions, Hadamard matrices, or linear shift registers. In this section, however, we will explain the method using Hadamard matrices and the symmetry of Walsh functions, both of which are used in the Qualcomm CDMA system. Each Walsh code in an orthogonal system has an equal number of identical and different bits when compared bit by bit. For this reason, the length of an orthogonal code is expressed as a power of 2, such as 2 to the power of m. Therefore, the smallest code is a code of length 2. A Walsh code of length 2, consisting of one identical bit and one different bit, must be, and thus, the smallest unit orthogonal matrix can be considered as shown in equation 2 to 20. Furthermore, when each element of such a matrix is treated as another matrix, it can be expanded as follows. A Hadamard matrix forms an orthogonal system through the expansion of the unit orthogonal matrix, as shown in figure 2 to 20. This method is utilized to generate Walsh codes that distinguish channels in currently operating CDMA networks. Another method of generating Walsh codes is OVSF, which is a method for creating supplemental channels to implement high-speed data. OVSF, as seen in figure 2 to 21, is a technique for generating code channels by adjusting the spreading factor. It stands for orthogonal variable spreading factor, meaning the spreading factor of the orthogonal channels can be variably adjusted. OVSF is utilized for code channel generation in 3GPP, asynchronous CDMA, commonly known as WCDMA. The orthogonal codes generated using the Hadamard matrix method, or the OVSF method, are identical. Only the indices of the codes constituting the orthogonal system differ. OVSF can be thought of as rearranging the code indices by grouping clusters of 1s or 0s together in an orthogonal code that is, into consecutive 1s or 0s. The code is constructed by keeping half of the codeword length, as is, and inverting the other half. Because of this, this method is also referred to as the bit reversal method. 2.4.7 Gold code. Gold codes are famous not only because of the name gold, but also because they are the codes used as spreading signals in 3GPP's WCDMA. Unlike PN codes, gold codes are not M sequences. A key characteristic of gold codes is that, despite being the same length, they possess significantly more generator polynomials compared to PN codes. PN codes have excellent autocorrelation, which allows for fast signal acquisition and tracking when applied as spreading signals. On the other hand, the number of generator polynomials capable of producing an M sequence for a given linear filter size is relatively small. For example, in a 15-stage LFSR, there are 32,767 possible generator polynomials, but only about 1,800. It is about approximately 5.5% generate M sequences. The fact that the number of generator polynomials capable of producing M sequences is very small for a given filter size is the biggest disadvantage of PN codes. To compensate for this, the invention of a new code was necessary, which was achieved by Dr. Robert Gold. Since these codes can be obtained through to independent PN codes, a large number of codes can be easily acquired using a relatively simple method. Furthermore, the correlation characteristics between the codewords of these codes are also favorable. A gold code is created by performing a bit-by-bit modulo -2 operation on the outputs of 2 meters sequences, P1 and P2, which are generated by different primitive polynomials. Figure 2 to 22. Since the length of a PN code obtained through an NLFSR is 2 to the power of n-1, and the bitwise modulo sum of 2 PN codes is also 2 to the power of n-1. The length of a gold code is 2 to the power of n1. Additionally, by fixing P1 and shifting P2 through 2 to the power of n-1 possible phases, 2 to the power of n-1 different codes can be generated. In other words, 2 to the power of n-2 codes are created, and by adding the original P1 and P2 to this set, a total of 2 to the power of n+1 codes can be utilized. Thus, the number of gold codes that can be produced is 2 to the power of n+1. For example, let's generate gold codes using 2 PN codes where n3. If the generator polynomials for the PN codes are p1 x cubed plus x squared plus 1, and p to x cubed plus x plus 1, we can create 10 gold codes as shown in figure 23. As can be seen from the results above, there is no possibility of a gold code being mistaken for another code, regardless of any phase shift. This can be predicted from the methodological characteristics of gold code generation. A gold code created by multiplying to Pn codes of finite field size n is a code that belongs to a finite field of size to the power of n. In this finite field, the length of an m sequence would be to the power of n minus 1. However, since the length of a gold code is only to the power of n minus 1, it is not an m sequence. Furthermore, it can be observed that in a finite field of size to the power of n, there are to the power of n plus 1 gold codes of length to the power of n minus 1. This is well illustrated in figure 24. Due to the vast variety of gold codes, logical differentiation between individual codes is possible. Therefore, systems do not need to share common reference time information. Consequently, the WCDMA system proposed by 3GPP does not require GPS information. This is why WCDMA is referred to as asynchronous CDMA.